Hey guys, I want to talk to you guys today about how to use calculus to calculate the length of a curve. So say we have a curve that looks something like this, and we want to calculate its length from say A to B. Then what is actually going to end up happening is that you're going to take these tiny distances that you can see I'm drawing, and you're going to look at how these distances change as the distance between them approaches zero. So we're going to use integration, and it's going to work a lot of the same way integration works, where we're going to look at this change in x, as you can see it here, this delta x, as it goes to zero. I have kind of this neat little thing pulled up. So you can see here we have a curve, and if you can look at this one on the left, you can see that that's not going to do a very good a job approximating the length of the curve. But as we increase the number of intervals, which basically decreases the size of the interval, then you can see that it's going to be a better and better approximation. And so what's going to happen is that the distance between these intervals, or dx, is going to go to zero, just like whenever you're doing Riemann sums and you're, approximating the area under a curve. And we're going to use kind of a version of the distance formula as those distances go to zero. I don't want to spend the time proving this formula for you. You can take a look in your textbook if you're interested in the proof. But here's the formula. It's just going to be the integral from a to b of the square root of 1 plus the derivative of your function all squared dx. The majority of these, because you have this square root around the function, are going to be functions that are not going to be easily integrable by hand. So the majority of these questions, unless it's something fairly simple that maybe can be like FOILed and refactored to be a perfect square, we're not going to be able to integrate these by hand, and we'll have to use the calculator. So let's take a look at this right here. Oh, sorry. So we're given this function. Y is equal to x to the negative 1. And we want to integrate this over the interval from 1 to 2. So if we take a look at the function, and we first want to find its derivative, because we're going to have to use and take the derivative and plug it into the formula. So y prime, this is x to the negative 1, so that's going to be negative 1 times x to the negative 2, or negative 1 over x squared. So now I'm going to take, and I know my y prime or my f prime of x, and so I'm going to plug it into this formula. I take a look at my bounds, and I see I want to go from 1 to 2, so I'm just going to integrate this from 1 to 2, and this is going to be the square root of 1 plus my derivative, which is negative 1 over x squared, all squared dx. And so I can't easily integrate this function. So what's going to happen is that I guess actually I could do it by hand, but it would take some, I'd have to get a common denominator and simplify and so forth. And so what's going to end up happening is that I'm just going to use the calculator, and I'm going to use Math 9 on the calculator to get the approximation for the arc length. Sorry, it takes a minute. All right. So I'm going to take, and I'm going to integrate from 1 to 2. And my function is going to be the square root, make sure you keep up with your parentheses here, of 1 plus, and then I have negative 1 over x squared. And then I'm going to square that. And then I'm integrating with respect to x. Does that look okay? Good to me. So the length of that curve over the interval from 1 to 2 would be approximately 1.132. So generally S is denoted as the length of a curve, and so I would say X is approximately, let's use approximate, 1.132. One thing that we're going to get into later is that the total distance traveled by, say, a particle would be length equal to its arc length. So that's one good application of arc length. Let's try one more example. So we're given this function, y is equal to 1/4 x to the fourth, and we want to find its length over, once again, the interval from 1 to 2. So the first thing I would do is I would differentiate. So this becomes 1/4 times 4 times x cubed, which just becomes x cubed. So now I'm going to take and I'm going to plug it into my formula. So I have the integral, s is going to be equal to the integral from 1 to 2 of the square root of 1 minus x cubed all squared dx. And then once again, this is not a function that's easily integrable without some algebra. So I'm going to go into Math 9. Going to integrate from 1 to 2. And so it's going to be the square root of 1. Let me check something really quick. Okay, I just misplaced the minus sign there. So definitely this should be plus. I apologize. 1 plus f prime of x all squared. So then this would be, let's go back here, 1 plus x cubed all squared. Or you could do x to the 6th. And so this length is approximately 3.925. So then I would say S is approximately 3.925. All right, it's pretty simple. This is definitely, we'll look at these applications more once we get into parametric functions and movements of particles. But I wanted to go ahead and introduce it to y'all now. All right, I hope that you have learned something. Thanks so much.